Okay, lecture 30 or 24 begins our discussion of infiltration. And I'm going to talk about the governing equation for infiltration, which results in something we call the Richards equation. And then we'll talk about some approximate infiltration model methods. The Richards equation is a partial differential equation, and we don't have an analytical solution to it for the most part. What we do is we have approximations to that. And so we're going to spend some time today putting together the green amp method and understanding how it's solved using something called the Mean-Larson method of solving the green amp equations and methods. We also have the Horton model, and I'm just going to introduce that. You will have a homework problem in it, but it's a fairly simplistic model so long as ponding conditions are occurring. We'll talk a little bit about that. Then there's this lumped abstraction model, which is basically just like it says, it's a lumped abstraction. It's a constant abstraction value, very simplistic. The last approximation method we're going to discuss in this class will actually be in next lecture. And we're going to talk about the NRCS rainfall runoff model, and that may be more commonly known as the curve number model. If we look at the hill slope, which is what this cartoon shows, you can see how water, when it falls as precipitation, you've got various modes, and as part of its disposition, you've got some of it will infiltrate through the ground surface. Down here, we've got the groundwater table, the groundwater flow. Out here, we've got the stream. And so what happens is when you have this precipitation, it falls, some of it infiltrates. It will come out as interflow or subsurface flow, end up in the channel. Some of it will go all the way down into the deeper groundwater in the water table. And some of it will obviously run off if the intensity is enough to create excess precipitation or precipitation runoff. A couple of things that you need to understand here. We've got this definition of groundwater flow. That's a saturated flow situation where all the void spaces down here in this in the geologic material are totally saturated. There's no air pockets. Where we've got subsurface flow and infiltration, that's something we call unsaturated flow, and this is the unsaturated zone. And so here's some other additional discussion about that. You know, unsaturated flow through porous media where some of the voids are filled with air, and that's what I just said. So a few definitions. Porosity of the soil, that's the volume of the voids divided by the total volume of the material. We've got soil moisture content, which is the volume of water in that soil divided by the total volume of the soil. And note that the maximum saturated soil moisture content is going to be equal to whatever our porosity is. That's the maximum you can have. Then we've got something we'll call the Darcy flux, which is the flow of the water down into the soil divided by a unit area of soil. So it's little q. We often talked about in open channel hydraulics, we talk about little q as being a unit discharge. This is kind of similar to that. That's kind of similar idea. This obviously has units of feet per second or meters per second or millimeters per second. You know, it's a length per time. And so that's called the Darcy flux. Hydraulic conductivity, it describes the ease with which water can move through the pore spaces or the fractures of the soil. Obviously, the tighter, you know, the clays, those kinds of soils are going to have a lower hydraulic conductivity or ability to allow water through their pore spaces than something like a sand substrate would have. There's another concept we need to talk about, which is this suction head, and that's the suction force that binds water to the soil. So when the soil is drier, it has almost a, it has a suction capability where not only is gravity driving the flow down through the soil column, but you also have this suction force that, that pulls the water through. If I look at the governing equations in unsaturated flow, you can see this is the continuity or conservation of mass for one-dimensional unsteady unsaturated flow and porous media. Here we've got the water content of the soil. This is the time parameter. This is the Darcy flux, and this is the vertical direction Z. So you can see that the water content, it varies with time, plus the Darcy flux varying with depth in the soil column equal to 0. That's the 1D unsteady, unsaturated flow and porous medium. Now, we've talked about the Darcy flux. I want to introduce the Darcy's law, which basically is the negative value of the conductivity, the hydraulic conductivity, multiplied by the head loss per the medium. And so the head loss is the head change over the depth, okay? This head is a function of the potential energy, but also the soil force that binds the water to the soil particles. That's the suction head we talked about. So when we talk about head in a soil, we not only talk about what is its elevation and where you're at in that soil column, but also what is the soil suction. And psi, the Greek letter psi, is the abbreviation we'll use for soil suction in this lecture. Now, if I look at the Darcy's law and kind of develop it a little bit, this is the Darcy's law. Remember, we said the Darcy flux is equal to minus K times dH dz. Well, we've expanded that a little bit. We've said that that head is the soil suction plus its location. If I go through and do a little bit of manipulation on the differential there, I can look at the differential of psi through the chain rule, and I can say that's d psi d water content theta d theta dz. That's just breaking this apart in the chain rule. We call that the wetness gradient, okay, is this value right here. And this is the reciprocal of the specific, what they call the specific water capacity. That's just a definition. If we use that in this derivative, plug that in, we can restate the Darcy flux as minus this value D, which is going to be the soil water diffusivity, which is defined as this value here, times the derivative of how the water content of the soil changes with depth plus the hydraulic conductivity. Now, we got to this point right here. This is explaining the Darcy flux. Now, if we look further, we've got this Darcy flux. We also combine that with the 1D continuity equation for the soils. We can combine these two, and this becomes the 1D Richards equation. And so you can see what we've done here is we've left d theta dt alone, and we've plugged in for dq, or the dq, this Darcy flux value right into there, which ends up being this Richards equation here. Now, if the soil is homogeneous, which rarely happens, but if you could assume it's homogeneous, meaning that it has the same character throughout its soil depth, you can say that the change of that hydraulic conductivity with respect to distance is equal to 0. Now, we're not going to be solving this in our class. And what happens is we end up in hydrology having a lot of different approximate infiltration model methods. And as I mentioned, we have the green amped, the Horton's, lumped abstraction, and the SCS rainfall runoff method, which we'll cover next lecture. You are responsible for understanding these 4 methods as part of this course. So I want to give some more definitions. We've got something we're going to abbreviate as little f. That's the infiltration rate. That's a rate at which water enters the soil, which expressed in length per time, either in inches per hour or centimeters per hour for the most part. Then we've got the potential infiltration rate. That would be the infiltration rate if water is actually ponded on the surface of the soil, on the ground level, okay? And so if we've got an infiltration rate, that may not be the maximum potential infiltration rate. It only would be the infiltration rate equal that potential infiltration rate if I've got ponding occurring on the top of the soil. So it's not limited by the supply of water, in other words. So if I got plenty of water, the rain is falling hard enough, that we'll end up having enough water coming in that it can't infiltrate fast enough. It ponds on top. That means that that infiltration is capacity of the soil has got plenty of water supply at the top to drive it. We also have something called the cumulative infiltration rate. That's going to be capital F. That's just the integral of the infiltration rate with respect to over time. And so you can see, kind of from a theoretical standpoint, kind of what happens. I've got the ground surface out up here, and I've got rain or moisture falling on it. And so as we look through the soil column in the depth, this is going down into the soil column. We can look at the moisture content plotted on the x-axis here, and we've got depth plotted on the y. And you can see as we go down in depth, that moisture content changes. And so you've got the saturated zone up here at the top. And again, way down here at the bottom, we've got the water table somewhere down here. Okay, but between the water table and the ground surface, when it's not raining, that is unsaturated soils. And so there's air voids. So it starts raining, we get a lot of precipitation, and you start getting this moisture to change as moisture infiltrates into the soil. So we get this saturation zone. That's where the theta is going to be equal to the porosity of the soil. Basically the porosity being the number of voids, or the volume of voids divided by the volume of the soil material. And then we got this thing called the transmission zone, and that's the area where it's sort of getting wet because of the water that's infiltrating. And then at the very front of this, you've got the wetting zone. Now the wetting zone, all the way down here, even in this unsaturated zone, we have some value that is a base value of water content. The soil, unless you bake it in the oven, for a couple days, there's always going to be some moisture tied up in the soil column. And so we're never at theta equals to 0 usually, unless, like I said, you're in the the Sahara Desert or somewhere where it hasn't rained in a year, or you've baked it in an oven. And so if we look at this infiltration rate, and so as you go through time here, and this is infiltration rate plotted in on the y-axis. And so here in red, I'm going to plot the infiltration rate. You can see that as time goes on, we've got, we decrease in our capacity, our infiltration rate, because the soil becomes saturated and it's harder to get that water in. So that kind of makes sense. If I plot in, let's get a different color here going, hopefully. I'm having trouble changing. I thought I could change colors on this. Yeah, there it is. So let's try to change to different color. So we'll use blue. And so now if I want to plot the cumulative rainfall, or sorry, cumulative infiltration, I can plot that here in blue. And again, that is the integral of what's under this red line here. So if I've got a point here, which is at time t is equal to 1, if I look at that, again, let's get this back up here and change the color back to red. If I look at that, that value would be equal to whatever the area is under this infiltration curve. So remember, the F is equal to integral of the little f, right? So that's just the area. So this value right here on the infiltration curve corresponds to the area underneath this curve here in the crosshatching. And so, kind of an important point to make. If I go along here and I say, okay, well, I want to know what the infiltration, cumulative infiltration is all the way over to this time. Well, I just take the total area underneath that, and that's equal to this value right here. So this is my infiltration, total cumulative infiltration. This is an infiltration rate. And again, on top of this, we've got the hyetograph of rainfall that's laid out here. And so if this is my rate of rainfall I, let's change that color there, where you can see that maybe a little better. We'll change that to green. So if I've got a value of the rain that's in I. And so here is my rate of rainfall for this time period. The difference between the total infiltration, intensity of the rain minus, let's take the average infiltration rate across there. That above it would be my rainfall excess, and that below it would be the amount that is infiltrated. And so long as I've got rainfall rates that are occurring at a larger value than the infiltration rate, this is a fairly simple computation for the most part. And if you're using this a lot, is like the Horton's method. They will actually have a description in the Horton's method of what this curve is. And so then you'll be able to look at the curve through time and basically make a computation of what would be the excess precipitation. And the homework problem, one of the homework problems for Lecture 24 is to actually do that. There's also a bonus lecture slides that tell you how to do what happens when you have rainfall that starts out lower than this infiltration rate capacity curve. Well, you're not going to follow this curve because there's capacity that's still in the soil column, so you have to do some adjustment. But that's a kind of a bonus thing. I'm not going to require you to know that for the quiz purposes or exam purposes. All right, so if I look at the green amp method, if I look at this as remember how we had the actual wetting front, and we had the transmission zone, the saturated zone, etc. With the green amp, they basically use this this piston type of what they call a piston model. And this theta I down here, that's the moisture that's sort of at the initial point. That's without any kind of infiltration. That's the resident, the ambient soil moisture that's present in the soil. And again, we go back to this Darcy's law here, and we've got this value. If we look at the total saturated value of the soil, that's going to be the porosity value in. And if we look at this, we can say that this Darcy flux is analogous to the infiltration rate, right? Because this has units of length per time. Infiltration rate has length per time as units. And so if we use Darcy's law, we can say that Q is equal to negative F, because positive Q would be going up, negative Q is going down. So if we've got positive Q, we have to end up having negative F, which allows us to get rid of this negative sign right here. So as we go down here and look at breaking this apart, where we approximate Q is equal to F there, we get rid of the negative sign, so we carry the hydraulic conductivity down here. And then we get into this dH dz. And remember, I've talked to you about, the differentials. That's analogous to delta H, delta Z. So what is the change in head over some distance, delta Z? And that's what we've got here. So if we have point 2 being here and point 1 being here, the delta Z would be this distance here, right? And here's my point 1. And so I've simply got delta Z is equal to L. So then I've got L is this Z1 minus Z2. And then if I look at my H and I say, okay, well, that's going to be H1 minus the H2. So here's point 2, here's point 1. Well, what is the head at point 1? Well, if we've got ponding on top, we can call that H sub O. That's the value of ponding. And then what is this down here? This is a negative distance L. So it's minus a negative L. And then we'll also have this suction head minus the psi. And so we end up being able to look at, the suction is pulling it downward. So that's why you get the negative value. The negative L gives its position in space. If this is my datum here, 0, well, this is minus L distance down. So we end up having our Darcy's law turning into the infiltration rate is equal to K times HO minus, then in parens minus psi, which is the soil suction, minus the distance L over the distance L. So again, carrying this over to this, we can see that F, which is the total amount of infiltrated water up to a certain point, F is equal to nothing more than L times delta theta, where delta theta is equal to N minus theta I. This is, again, this delta theta I'm talking about right here. And so as we move through this, we can see that getting rid of some terms here, we can simplify and pull some things together when we start looking at this value to our equation 4 here. This changes into this F is equal to K times psi delta theta over the value of Ft, where that's nothing more than F is equal to L times delta theta, right? And so, or L is equal to F over delta theta, right? And so we plug that in here. So this is equal to F over delta theta, and this reduces to this. So this is a form of the Green-Amp method. We're going to call that equation 4. Now, if we've got equation 2 is this integral of the F dt, if I plug in what I've got, and I take this equation here, equation 4, and I take the integral, I plug that equation 4 into here, I can get a Green-Amp equation for cumulative infiltration. This is going to be our equation 5, which is going to be used when we use the Meyn-Larsen approximation. These are going to be things that you're going to be using to solve practical application problems. Now, you'll note that this is nonlinear implicit, meaning that you've got F here bound up here, and then we've got it kind of embedded, and so you've got to work on this. You also note that you got capital F, which is the cumulative infiltration, and you've got the infiltration rate. So this becomes a kind of a problem that we have to use successive approximation to actually solve the problems. And we'll see through the Meyn-Larsen approach how they do that. If I think about estimating soil suction, this is a table that I've put together from a couple different sources. And this is basically different types of soil type. And then you can see what their porosity is. You can see kind of the range in porosity. This is an average value for sand. And then you've got this effective porosity, and you've got the wetting front soil suction. That's a term. We've got hydraulic conductivity. We've got something called field capacity and wilting point. The field capacity, we've got these defined down here, which is the field capacity is the residual water content after gravity drainage. And then the wilting point is the limiting water content below which plants no longer can have transpiration. All right, so the original Green-Amp model built for conditions where rainfall intensity always exceeds the infiltration capacity. So when we talked about this right here, we always have some ponded water here and in the original model, but we don't always have that. So the Meyn-Larsen approach is what we'll use, because we have rainfall rates that will be different, lower than the infiltration capacity. So there's not ponding all the time. So we have to figure out how to deal with that in a practical application. The Meyn-Larsen approach takes the equation 4 from the Green and Amp discussion and essentially says there is going to be some point in time when there's going to be surface ponding occurring at some time later due to the rainfall intensity. And so we're going to work through that and see if that will work, and then look at the timing on that. There's some trial and error things that we do, and there's a little bit of complications. It's not easy to understand exactly how to work these Meyn-Larsen, but I'm hoping through both the kind of the steps I give you in the slides, plus also the example problems, you'll be able to figure it out. It's sort of one of those things where actually doing it helps, and looking at what the problems mean or what the equations mean kind of helps you kind of reason through this. This F sub P is the cumulative amount of rain when ponding begins. And then to compute that time to ponding, that's nothing more than the value for F sub P divided by the intensity of the rain that caused that ponding. So that's equation 7. Equation 6 was the one we discussed before. And then equation 8 is looking at the infiltration values. And so if the time is less than the time to ponding, that infiltration, that means if it's not ponded, every bit of the water that's falling out of the sky as rainfall intensity, that's going to be equal to the infiltration rate. If you're greater than the time to ponding, well, then we're going to go back to this equation that was derived as part of the green amped equation. That is the infiltration rate capacity. And again, that is back to right here, this equation right here, equation 4. And so that's what we've got. And all right, so delta, I want to point out, I call it delta theta here. Here, we're actually using nu minus theta I, where again, this theta I is equal to the initial water content in the soil. Now, if we look back at equation 5, which is that cumulative equation that we have for green and amped, again, equation 5 is setting right here. This is equation 5, back a few slides on slide 14. We will note that Mine and Larson formulated this approach, which says that instead of using this straight up as T, because that would assume that ponding had begun from time at when ponding, you know, when we first started getting rainfall, we would have ponding from the get-go. Well, they realize you don't. So they've got this T and they subtract off the time it takes to actually get ponding, T sub P, then they add back in, well, if they had that rain coming down at a certain rate, or that I'm sorry, that amount of water that got infiltrated, how long would it take if there had been ponding at the beginning? So this is sort of their, you know, kind of their way to deal with this, and they put this in, and then they basically then everything else looks like equation 8, not 8, but equation 5 did prior. So you've got the second, this is the delta theta, and this is, again, the soil suction. This is the cumulative infiltration rate. Again, it's here and here. So this is, again, through successive approximation, we have to go through and solve this. Delta theta, and again, this is soil suction. So again, this is defining T P sub prime is the equivalent time to infiltrate F sub P from equation 6 if ponding had existed from time is equal to 0, from the get-go, as I said. Now, the Mine and Larson approach is very simple if I've got uniform rainfall intensity and it's above the infiltration capacity. It's a fairly simple thing. You've got equation 6. You basically use equation 6 to calculate your F sub P, which is your cumulative infiltration at the point of ponding. And then, so again, this I misspoke there a little bit. I said that this is assuming that I had enough rainfall intensity that was high enough to have ponding from the beginning. That's not necessary. This is just for uniform rainfall intensity. So I misspoke. T sub P is computed. That's the time to ponding for this this value that you compute in equation 6. You use equation 7 for that. And then you calculate this T sub P prime, which would be the time it would have taken ponding to occur if it had been ponding from the beginning. Value there, so that's equation 5. And then you develop a relation. So you go to equation 9, which I said was this this thing where I've got time embedded in with F on, in sort of a very it's an equation that you can't just directly solve. And so typically what I do is I take equation 9 after I've gotten T sub P and T sub P prime, and I'll develop a spreadsheet that'll have various values of T and various values of F. And so I'll assume, actually I'll put in a value of F. Oops, sorry about that. I'll put in a value of F into that equation 9, and then I'll say, what is the T that corresponds to that F? And I go all the way through, and I just develop a relationship between T and F. That way it's sort of like a lookup thing. Well, if I have a particular time, I know automatically what's the F based on these foundational time to ponding and time to ponding prime. And so that's something that you'll do. And you'll see that when we get into the, I'm not going to work an example problem for uniform rainfall intensity because that's fairly straightforward. It's more complicated when it's non-uniform, which we'll talk about in a second. And then I compute the F for each capital F using equation 4. So you'll go back to equation 4 and compute the values of F and capital F, so you can actually, look at that, come up with a formulation for that. And then I have to basically, here's the kind of the equation to think about and keep in mind, is that what I'm after in each time increment of rain, I'm actually after what is the excess precipitation in that time increment, because that's what I'm actually going to plug into my rainfall runoff model as what's available to run off into the receiving waters. And so that's delta P sub E in this time increment. And then I've got the total rain that fell in that time increment. I've got the amount that was infiltrated during that time increment. And then I've got something called the change in amount of surface retention storage. That's also known as depression storage. So if you've got to set that value, what is the value of S, which is your amount of total depression storage that your watershed has or needs before rain runoff can occur, and that value, and we're going to use an example in a little bit, but I'm going to use an example that S is going to be equal to 0.5 centimeters. It kind of gives you an idea of the scale of that. And so you have to track how that's changed. If I've got delta S less than, if I got delta S changing such that you are not going to have any ponding, or you've still got amount you haven't satisfied your total value of S. Well, there's no way you're going to have precipitation excess. So we're going to talk about that when I get into this non-uniform rainfall intensity problem. So this is kind of a step-by-step procedure that we follow, that I've made up basically from looking at various textbooks and how they solve things. I try to put it into a step-by-step procedure, and I'm hoping this is helpful, sort of as a run through, starting at step 1 and sort of like a nested thing where you go through. And so the first thing in step 1 is if your intensity of the rainfall I is less than your hydraulic conductivity of the soil, you're going to have total 100% precipitation or infiltration. None of it's going to run off because it's all going to go in the ground. And so we're going to keep track of that. So if you're in the first time increment, you look at that, you've got an I less than K, well, it's going to not have, you're not going to have any runoff. It's all going to infiltrate, but I'm going to keep track of it. And then I'm going to keep advancing through my time steps until I get to the first increment of rainfall intensity that's greater than my hydraulic conductivity K. Okay. Once I've got that, I go into step 2. And then I follow these processes. I just basically solve things. I solve F sub P using equation 6, and then I calculate something called T prime, and that's defined right here. So I use this F sub P, I plug it in there. I've got the increment of the rainfall intensity for my current time increment. That's the I value, I sub I. And then the T prime is what I'm after. And then Fi minus 1, that's all the rainfall that's all the infiltration that's infiltrated prior to the time step you're in. So if there were 2 or 3 time increments of rain that went into the ground in step 1, you need to, as I mentioned, you have to keep track of those. You need to keep track of the amount of infiltrated rainfall, because that's going to be this Fi minus 1. Okay, Fi sub I minus 1. And so as we go through that, you calculate the Ti, and then you get this time to ponding Tp, and then you get the Tp prime, and then you solve for F, plugging that into equation 9, which uses the Tp and the Tp prime. And then the step 2.6 is where all the thoughts got to be. You've got to keep reminding yourself of this water balance. And you look and you say, okay, I'm really after this, but what I first need to do is look at what's available to me in this time increment as far as rainfall that could either run off as excess, delta PE, or it could get stored as detention storage. So the first thing I do is I look, what is my delta P? Well, that's just my rainfall that's fallen in that increment of time. So that's I times delta T. And then my delta F is equal to the F that's fallen in this, so the F that's the value of the total infiltration at this time step minus what was the F that infiltrated, total cumulative infiltration in the previous time step. So then I typically do delta P minus delta F. I see what that value is. Examine that. Now, if this value is positive, first of all, it better be positive or you won't have any chance for any kind of excess precipitation. The next thing I look at is, what is the S? Have I been tracking this? If this is my first positive value of our rain that's actually had an intensity greater than the hydraulic conductivity, well, we've had no storage up to this point. So now I've got to satisfy storage. So once I get this value, I look at my storage. Let's say, for example, that I calculate this value was 1.5 centimeters. Well, then I would look, what if my storage, my detention storage on the watershed was 0.5 centimeters. I would just basically say, okay, well, I've got to satisfy this. I take that out of that 1.5, which leaves me with 1 centimeter extra. Well, if I look up here at my conservation of mass equation, I know that delta PE is going to be to that 1 centimeter then, right? Because that's the only thing that's left. I've got the delta P, I've got the delta F, I've got the S, which is now the delta S is equal to what my 0.5 minus what it was S in the previous time step, right? And we've had none, that was 0. So my delta S becomes 0.5, which is, I subtract that off 1.5, and that all lends itself to 1 centimeter. And so that's what this paragraph here kind of discusses that, and I think it may become clearer as you look at the example problem. Now, so I've had one increment of rain that was higher, in terms of the intensity, greater than hydraulic conductivity. I do that, I get to the end of step 2.6, and I go to step 3. And so I go and look at step 3, and I notice that, well, I use equation 9 here with the existing values of T and T sub P prime. There's a paper, a chapter in your references that's by Skaggs, who was at North Carolina State University, but he wrote in a textbook that I have called Hydrologic Modeling of Small Watersheds. And he talks in there, he shows some research, I can't remember the exact research paper that he referred to, but it basically said that the infiltration, cumulative infiltration relation to infiltration rate is very insensitive to the intensity of the rain. And so we take advantage of that by saying, even if in successive steps, the rainfall may fall off enough that we actually start to drain or we even lose our retention storage, we're still going to be able to get away with using the same TP and T sub P prime that we computed in step 2. So I'm going to use this equation 9, and I'm going to calculate a new value of F, and then I'm going to subtract that F from at that time step from the F at the previous time step, so I get a delta F. I calculate a delta P, and again, I repeat that process where I say, okay, well, delta P at this time step minus the delta F, that's the excess water potential that I have. And then I look at my storage. Did I have storage, my detention storage, was it full from the previous time step? If it was, then 100% of this difference goes to delta PE, or my excess precipitation. If I didn't have my storage full, then I have to satisfy that. Whatever's left over is the delta PE. And so you just keep proceeding through this, and step 4 talks about that, repeat step 3. And then this note down here was what I was talking about when I was talking about the reference to Skaggs. You can look at that. Let's see. If you look at page 145 of that, I think I referred to it as Skaggs. It's chapter 4 in hydrologic modeling of small watersheds. It's actually in Canvas. You can kind of see that there. And so it kind of discusses that in case you have any interest. All right, so that's the Mean-Larson. You're going to have to look at your at the example problem to see how things go there. Now, I want to move over into the Horton method, which basically, as I already mentioned too, I've got this curve that describes the infiltration rate versus time, and this curve is this F sub t here. And that curve is described as F sub c, which is a constant, what I call the terminal value of infiltration. So it's it's a constant out here. So this is the F sub c, that value, and that's plus F sub o, which is an initial infiltration rate, which is right here, F sub o, minus that FC again, times the exponential of minus KT. This K is a decay constant. And so this is an exponential decay, which describes this. And again, if your rainfall intensity is all above that curve, it's simply then whatever that intensity of the rainfall was minus whatever the average infiltration rate is between the two. That value above it's going to be the excess precipitation. Again, same thing here. You know, this is the excess. Same thing here. This is the excess. Same thing here. Now the problem is going to be. Let's see. Try to get this up here. Try to get my eraser. This very thing that's shown here, the problem is, what do you do when you've got rainfall rates that are lower than the actual infiltration rate capacity? That means we've actually got unfulfilled storage in the column, in the soil column. And the same thing here. And so what's going to happen, there's an adjustment procedure. I've got a bonus lecture that you go through, and you can actually adjust and come up with a new curve that fits in over here. And so this is an adjusted Horton curve. And there's a whole process to do that. And I've got an example in the lecture. I've got the notes how to do that. All right, so these are the values, just kind of giving you some ideas of initial infiltration rate. This is the constant, the value of the constant infiltration rate at the bottom when it gets to equilibrium. And then this is the decay constant. You can see here are values based on the types of soils you're talking about. And again, these are in millimeters per hour. Now, the lumped abstraction method, you know, where we had this, which we recognize as kind of what really happens with the soil in terms of the infiltration rate changes with time. This is what the lumped abstraction does. It says, oh, I've just got a constant value phi. And so what you do then is if you have a hydrograph of rainfall, you would take that phi, and everything above it is excess, everything below it infiltrates. It's a very simplistic method. And there's a phi index discussed in examples in lecture 27, although I've got to check that. I've changed some of the lectures. That may no longer be part of lecture 27. Just have to look. All right, as we mentioned, the next lecture 25 is going to talk about the NRCS rainfall runoff model. But again, that's, you know, we're talking about excess precipitation, much like what we talked about with the Meyn-Larson approach to green amp. Same kind of concept here. We're looking at excess precipitation for each time increment. And we've got things that are a little different here. This is a very simplistic method. That's why it's so popular, is you've got this curve number method where we've got the maximum storage. And I'm going to get into this in lecture 25 and talk about it. But it's the maximum, you know, it's a storage on the watershed. And that's going to be, that storage is going to be a function of something called the curve number.